It's a pleasure to welcome the next speaker, Jiagang from UFF in Niterói, and he's going to talk about measures for maps that factor over Anosov.
Okay. I would like to take this chance to thank the organizer's invitation to have this chance to say happy birthday to Lorenzo. Yeah, I really would like to say this to him because when I was a master student at Decay University, that was 2003, and Lorenzo gave a talk at Decay University, and then I decided to come to him immediately after his talk. Yeah, he helped me a lot when I applied fellowship from him. Okay, and in the first year when I attended IMBA, he and he gave a fantastic course about the partial hyperbolic for one semester. That's one of the best course I ever heard, because the whole semester they only talk about papers, whole semester, from blender, robust transitive, dominant stability, minimal foliation, and it's crazy because every 2 weeks they talk one paper. So yeah, and I learned a lot from that talk. So today I will going to talk something similar for partial hyperbolic, the unstable foliation, but it's from different way. It's from the ergodic theory part direction. So the talk is about today the topic I'm talking about is the measures of maximal u-entropy for maps that factor Anosov. So we are talking about a partial hyperbolic diffeomorphism. That's quite a standard. So we have two boundaries. So we have the unstable boundary and we have the center stable boundary. Okay, this is quite a standard definition. And we assume all this partial hyperbolic diffeomorphism to be dynamically coherent. So dynamically coherent implies the CS boundary is integrable. The unstable boundary, of course, by the stable manifold theorem, it's always uniquely integrable, and we have a stable foliation always. So we would like to say something about the unstable foliation. Okay. Because unstable foliation is a part, we have a uniform hyperbolicity still. So the first, we would like to see the entropy. The first definition is a topological u-entropy. The topological u-entropy was defined by Raul and Jeff Shah. It means we take any disk inside the unstable leaf, and we take the iteration, we see the volume, growth speed. So essentially, this definition is not new. It has been used by Youngling when he proved the entropy conjecture. He defined this, and later this was used by Gromov. Okay, but for the foliation, it was defined by Raul and Jeff Shah. And we also would like to see the metric entropy. The metric entropy is we have a partition. Okay, I don't want to see what means the partition subordinate. It's a partition with interior containing inside the unstable leaf and its Markov. So then we can define a entropy, u-entropy for this foliation. This definition has been defined a long time ago by Ledrapier. I'm not sure if Pessin has defined this or not. Okay, but at least in the 79, Ledrapier has already used this. Okay. So then we would like to ask if we still have the variation principle or not. Okay, because for this u-entropy, many properties we still have, like the row inequality. We have still the row inequality. So u-entropy less equal to the sum of unstable experiments. Okay, we still have the metric entropy less equal to the topological entropy. Then if we have the equality, we see these measures by measures of maximal u-entropy. It looks like this topological u-entropy, metric u-entropy are just our variation principle something. It's only all kind of definition. You just change the definition, give more restrictions, but in fact it's not. Because u-entropy, by this year's work, we know that u-entropy is a very powerful tool. It not only works for entropy, it works for rigidity theory. It's very powerful to prove robust transitivity. For instance, Lorenzo attractor, it contains periodic orbit for any dimension. It was solved by entropy theory. It's not proved by thermodynamic system. It was proved by entropy theory. So the entropy theory effect is a very powerful tool. Okay. So by Hua, Hu, and Wu, they prove that the measures of maximum u-entropy is not always not empty. We don't care about the single dimension. It has tangents and it's always not empty. It's convex and compact. The extreme points are always ergodic. Okay. So today we are going to show we are going to give some ideas or some situation we are going to show how we are study this space. So our main aim is first, we are trying to ask you some general questions. When this measure space is a finite dimension, in another word, it means when we have only finite many ergodic maximum u measures. The second question in general is we would like to ask if the ergodic maximum measures have some statistical properties like a center limit theorem, Decay correlation, some other stuff. And the final object is we are trying to understand the relation between the maximum u measures and some topological information of the foliation. It makes sense because this measures from the foliation. We would like to see if the measures can back to help us to understand the dynamic behavior of the foliation. Okay, so this part, there are two ways we want to see. One part is from dynamic system part. We are trying to see if it's a minimal or some other stuff. Another is from the foliation theory. Because for foliation theory, we know that the unstable foliation, the expanding speed is always polynomial. The volume speed, volume growth of the leaf for foliation theory is always polynomial. This was observed by Gromov and Sullivan. So the Planck's result, it always have transverse invariant measure for foliation theory. That's invariant by the holonomy map of the foliation. So we are trying to understand if this measure can help us to understand the transverse invariant measure that's not invariant by dynamic, but invariant by holonomy. Okay. So that's our main topics we are going to explain for some very special system. So we are going to start a kind of maps called factors of Anosov. Factors of Anosov, they contain many examples, and in the end of today's talk, I will explain several examples. F is factor of Anosov. First, it's parabolic, and there is a linear hyperbolic automorphism on torus, such that we have semi-conjugacy between F and A. We have a semi-conjugacy. This semi-conjugacy, it maps the strong unstable leaf of F to the homomorphically to the unstable leaf of A. So this is semi-conjugacy. Maybe you have several unstable leaves to the same unstable leaf. It's okay, but in each unstable leaf, you should be homomorphic. And the second is map the center stable leaf of F to stable leaf of A. Okay, so this means what it means a factor of Anosov. Okay, by this homomorphic, so we can take the Lebesgue measure on the unstable leaf of A back to a reverse measure on the unstable leaf of F. So in every unstable leaf of F by this homomorphic, we can define our measure. This is a reverse measure. Okay, so this is the systems we are going to start today. Okay, so factor of Anosov, in the beginning, let's try to think about a very simple example. If we have Anosov diffeomorphism, torus, then you consider cocycle. If you consider tangent map, the cocycle, you have a skew product, it's a factor of Anosov. Okay. So since every unstable leaf, we have a reference measure. See, we have a reference measure induced by the linear, by the unstable leaf of A, you have Lebesgue by the map homomorphic pull back, we can define a reference measure on the F. This measure essentially is a Margulis measure. It's a Margulis measure, and it has a constant Jacobi, but it's induced by the semi-conjugacy. So then we define a invariant measure mu of F is called C Gibbs state. This C Marcelo given this name because he said this C is constant Jacobian because our reference measure has constant Jacobian, so he prefer called C Gibbs state. If it's conditional measure along the strong answer block is exactly the reference measure. Without the Jacobian is exactly the reference measure. Okay, so first for faculty of Anosov, then any mu measure with maximum u-entropy if and only if it's a C-Gibbs state. Okay, this is the general result. So at least now we know, okay, the measure with maximum u-entropy, we know at least what it looks like in the u direction, because the reference measure is the exact measure, pull back the bigger for the A, and you pull back the reference measure. But the problem is we need to put, in order to answer our question of finiteness, we need to put some hypothesis on the transfer direction. We need to put some hyperbolicity. Otherwise, you could say Anosov times identity. It's easy to see there are examples with infinitely many maximum u measures. Okay, then we consider a special class of examples called the same most contracted center. This was modified by the system studied by Bonatti and Viana called the diffeomorphisms with most contracted center. Here, because the same most contracted center is every answer block, we have hyperbolicity on some polymer subset. But this is only respect to the reference measure. Okay, so we have this kind of hypothesis. Then we have finiteness. Okay, we should be careful about the regularity. Here we only need a C1. We don't need a C1 plus alpha. So every F C1 diffeomorphism, factor of Anosov, and has C most contracted center. Then we have only finite many ergodic measures with a maximum u-entropy. Okay, this part is still in the part of ergodic theory, but very soon we are going to see that every support of this measure has finitely many kinetic components. There are unions of unstable leaves. Every leaf is dense, so it means every measure is a support has finitely many kinetic components. Every component is a minimal set. So this part is for foliation. Okay, so we started from a little hypothesis of hyperbolicity, and we have the finitely many measures, the ergodic theory part, and then we have a consequence of the foliation theory part. We have a support has a finitely many minimal component. Okay, so now we partially answered our first question about the finiteness. And then our next question is we want to ask where are the measures, how this measures looks like. Okay, so we have the topological object called skeleton. Okay, this is something different. Skeleton is a set of periodic points, nothing related with measures yet. So skeleton is for partial hyperbolic systems. We have several finite set of periodic points. The stable dimension is coincided with the dimension of the CS bundle. And every point is strong unstable leaf. We are cut the stable manifold of some points, the orbital some points. And between these different points of the skeletons, they have no heat intersection. Okay, so this is a topological object. And but this skeleton can help us to understand the geometric structure of the measures. Suppose F admits, okay, suppose with same hypothesis theorem B, so it has factor of Anosov with seamless contracting. It has some skeleton, and the number, so this is topological information about skeleton, but the number of measures are the same with the number of skeletons. So the quantity of the periodic points of a topological object can tell us how many measures we have. And moreover, every ergodic measure, C-Gibbs state, is supported on the closure of the strong unstable leaf of the periodic point. So if we see the unstable manifold, we can know where the measure is. Okay. So this topological object can help us to understand what measure there looks like. Okay. So this theorem B and theorem C can tell us that, okay, we have finite many and we know what it looks like. So theorem D to tell us, okay, we have exponential decay correlation. Okay, I don't want to see what is this, to see more details here. Okay, so the principle says that, okay, we have exponential decay correlation. We should be careful because here we only assume the map to be C1. We only need to assume this map to be C1. Okay, so okay, we have the decay correlation, exponentially fast.
Sorry, Jiagang. These measures in this statement, they are also physical measures?
No, it's different. It's
because
only
of the
measures with maximum u-entropy.
But this has something to do with the regularity that you're assuming, because you said that they are only C1.
No. The reference measure in general is not irregular in the unstable leaf.
Okay.
So what are the examples of these C Gibbs measures?
I will give the explain. I will should be quick because in the end I don't have enough time in the end.
No, I mean, just to stay with the previous statement, I also was confused with the skeleton. Is this a symmetric definition? The U and S, so they are the
symmetric because for any energy.
Okay, so there's this like homoclinic relation between the.
It doesn't intersect.
They don't intersect. Okay.
They don't intersect.
Yeah, it has no intersection.
Don't intersect.
Okay. So we know that this is statistical property.
Sorry, Jiagang. This skeleton is the same one as the skeleton of defined by Ures and Catherine.
No, it's a little different. It's a little different. Okay.
But they give another name.
But they could be like, they could intersect that the unstable could intersect the stable of one, but not vice versa. Yes.
Okay, I'm not sure, but I think that should be different. Okay, you should blame Marcelo because Marcelo gives this name. Okay.
Oh, they're different. No, of course they're different.
Yeah.
They're related, but
so I will try to talk about the quite strange part, funny part. Okay, I will try to take more time to explain here. So this measure can help us to understand transverse event measure. So first, let's try to explain what means transverse event measure. So we know that diffeomorphism. These measures are evaluated by the diffeomorphism. Diffeomorphism, they change the unstable leaves. In general, right? Diffeomorphism changes the unstable leaves. They map one unstable leaf to another unstable leaf. But there is another kind of measure called the transverse event measure. What means transverse event measure? They only survive on the unstable leaf. No, in the transverse direction. There's some measures. If you consider the holonomy, okay, and then you have any disk, trans disk, you have some kind of measure that maps one to another one, invariant. So this transverse event measure only considers holonomy inside the leaf. They don't change the leaf. This is basically from the foliation theory. Okay, so then this term said, if F is parabolic factor of Anosov, then every measure with maximal u-entropy, they define a family of transverse event measure. So we could define, associate this measure with a transverse event measure. What means the transverse event measure is defined? It's like the following. You consider Gibbs state here, you do a quotient along the disk, transfer disk, you do a quotient. Okay, you get a measure here, and you times some uniform constant, and then you get a transverse event measure. So this explains to us the Gibbs state can define a transverse event measure. And then moreover, we have some very special, strange situation here. It's like the following. Suppose F is C1 plus alpha. Here we need C1 plus alpha. Here is the only place we need C1 plus alpha in the whole talk. A factor of Anosov, and we see most contract central. We take mu be an ergodic maximal U measure, u-entropy measure. Suppose whose support is connected. If it's not connected, you take it has a finite connected component, you take some power. Then for any unstable block inside the support and any section, then you consider the iteration of this block go forward. You see the intersection with S. you see how this intersection distribute along this section. They said that this convergence of the distribution intersection will converge exponentially to the transverse invariant measure defined by theorem E. Okay, let's see a picture. The picture is here. You consider any answer plug. You take any iteration, for instance, okay, it's a very, very long. You have many intersection points with this S. Okay, every point you take the atomic measure, you take the average, you sum all this atomic measure for this intersection of Fn Cux with this plug. You take this number of intersection and divided by this number sum of the atomic measures. This measure converge exponentially to the transverse invariant measure defined by theorem A. This is something quite strange because in general, in the formation theory, we don't have the speed of convergence. Okay, so this result really explains to us the C-Gibbs state. So for unstable formation, it's important for dynamic system. It should be important for formation theory because it has good hyperbolicity. It has polynomial volume growth, speed. It has transverse invariant measure, but we have no any way to study this transverse invariant measure. But now we know, at least for factor of Anosov, the maximum C measure is really a good bridge to build the connection between ergodic theory and formation theory. Okay. So any questions? Then the rest time I will talk only about examples.
Could you go back to one slide? What is this measure mu hat again?
So mu is a measure. Mu hat is a quotient along the plot. You do a quotient. Is you do the projection. This is the mu. You do the projection along to this plot. You do the projection along the unstable leaf.
S is a transversal to unstable.
Yeah.
Deviation.
Yes.
Okay.
And you should time some weight like Ci before.
Okay, so you do local disintegration.
So this implies that the C maximum U measure is really a good bridge to between the unstable formation for dynamic system and to the formation theory. May I continue?
Yes, sure. Okay.
So we have many examples. So first example is T3 diffeomorphism derived from Anosov. So we consider linear Anosov A with 3 eigenvalues, K1, K2 less than 1, and K3 larger than 1. So any parabolic diffeomorphism with 3 bundles, okay, sorry, here parabolic should be 3 bundles here. With 3 bundles as topic to A called derived from Anosov. So by standard result of poetry and Andy, every F here is dynamically coherent, factors of Anosov, and by work of Raul and my work with Marcelo, we could show it's a seamless contraction. So this means every F here has a unique maximum measure of u-entropy. Okay, and so in this case, you can see to compare to this result. So this one, any unstable leaf, if you take the iteration go forward on the transverse direction, it converges exponentially to some stationary, not transverse invariant measure. The second one is a parabolic diffeomorphism with circle 5 bundle. Okay, so this Lorenzo has a lot of important work about this area this years. So we consider C2 parabolic diffeomorphism accessible, dynamic coherent diffeomorphisms with a one-dimensional center and the center form circle bundle. Very special example is if you consider 3-dimensional near manifold, which is not a T3. It was proved by Poetry and Andy. Any parabolic diffeomorphism here belongs to SPH1. So it's a factor of Anosov.
Oh, sorry, Jiagang, you previous slides showed you have C1 And then you move to C2, or what?
Okay, so sorry.
What
So
is
all
that
this
is
previous, so all the previous result only need C1. Here C1 is enough. C1 is here C1 is enough. But in the next theorem to prove this example, I need C1 plus alpha or C2. Okay, so any F in the near manifold, not T3, if we have parabolic, if we have one periodic point, if it has one hyperbolic periodic point, okay, you have a seamless contracting. And in this situation, every ergodic measure of maximum u-entropy coincide with the maximum measure. The third example is a solenoid, topological solenoid. Let's recall the small solenoid, this small solenoid standard. So you have a solid torus, you have S1 times D2. On the S1, you have uniform bending, and on D2, you have contracting. So this is standard small solenoid, quite standard. Now we talk about the topological solenoid. Topological solenoid was first introduced by Bonatti and Mindy and David Yang. It's only with the same shape. So okay, on the circle, we have expanding, uniform. But the same on the transverse, on the vertical disk, it's not contracting. It's not contracting. Its shape, it looks like a contract topologically, but it's not uniformly contracting. Its derivative is less equal to K or large equal to 1 over K. It's a partial body, but not uniformly contracting. Okay. This case belongs to a system called a partial volume expanding. What it means a partial volume expanding? If you have any hyperplane which contains the unstable bundle, you have volume expanding. So this is a special case verifies the partial volume expanding. Okay, you could see this topological solenoid. It's really, you could have something very strange happen inside. You have some tangency, you could maybe have some source inside. Okay, every neighborhood embedding F has seamless contracting center. In this case, the space of significant space still coincide with the space of measurement with maximum entropy.
Oh, Jiagang,
Mm-hmm.
Just a question. Can you go back? So this factors over Anosov, this factors over kx mod 1?
Sorry?
This map factors over kx mod 1, k theta mod 1, not over the Anosov. Is this still the same class of examples you want to? Yeah?
Sorry, so you mean this example?
Yes.
No, this is so small solenoid circle, you have uniform expanding, vertical, you have contracting, right? So this is small. Topological solenoid, you have horizontal, you have expanding, but on this D2 vertical, you have topological contracting. You have the same shape, but this is not uniformly contracting.
No, I'm asking about the factor map, the factor, because the factor is not Anosov.
Ah, okay. So sorry. So this is not a factor of Anosov, it's a factor of uniform expanding. I'm cheating a little bit here.
Okay, thank you.
So indeed, you could build a semi-conjugacy between here to this small solenoid. You could build a semi-conjugacy between this topological solenoid to small solenoid. But the small solenoid, of course, it's not Anosov, but it's a uniform hyperbolic attractor. So this is should be factor of a uniform attractor. But the property is similar. Sorry, I cheated a little bit. Yeah. Okay, so the similar thing. So every embedding F in a C1 neighborhood has a seamless contract center. Okay. So there are all these examples. So now let me try to explain in a final place. Let me try to explain that why the U maximum measure should be important. There are examples with seamless contract center, factor of Anosov. The u-entropy is less than topological entropy. So all the previous three examples, the u-entropy equal to topological entropy. But there are examples, the u-entropy is less than topological entropy. And more important, the topological entropy is realized or achieved by the local House Schur. So this explains to us the global equilibrium state, the maximum measure is unfortunately is realized by the local dynamics, by local Horseshoe. You have the maximum value, but it's realized by local Horseshoe, local dynamics. Nothing for global hyperbolicity. The U equilibrium state is a local maximum because it only maximum along the U direction. It's called, it looks like a local maximum function, but it's realized by global dynamics. So I think that the U equilibrium state should be more reasonable to study for partial hyperbolic systems. Okay, finished. Yeah. Finally, I would like to thank you, Lorenzo, and I really appreciate your coffee. Okay, I think the Fuchs coffee is the best coffee I hear. Yeah.
Okay, thank you.
Yeah, thank you.
Are there any questions?
So Jiagang, what are the techniques that you use to prove exponential decay of correlations for these C1 maps?
Okay, so to prove this also, so the start is we need a back to a paper of, so for C1 map, the problem is like the following. Okay, so Dr. Biat, he has one paper to prove the muscle contracting for physical measures. And there he built the coupling. Built the coupling, but for these measures, only for the big measure, because it's physical measure. Okay, so because they need hard, because for the unstable leaf, you need to use passive theory to build the stable formation to be absolutely continuous. But here, we are lucky because our measure, reference measures, is from the Lebesgue. Our reference measure is from the Lebesgue. From the Lebesgue, these reference measures are invariant by center stable holonomy.
They are what?
Invariant by center stable holonomy. It's not only absolute continuous, it's invariant by center stable holonomy because it's induced from Anosov. Then we could rewrite all this part about the coupling technology. So we rebuild the coupling and use the method of Dogbiat. And there's another part, they need another C1 plus alpha, they need inside the unstable leaf, they need the distortion along the unstable leaf.
Yeah.
But we don't need it because we are Margulis measure, the Jacobi is locally constant. So essentially our proof is easier than his. Because with the hypothesis, the reference measures are too good in this situation. Okay.
Okay. Any further questions? Then let us thank Jiagang again.
Okay.